In this video, we're going to solve another example of a MM1 queuing system. Although the question is a bit long, we just pay attention first to all the important information about first, the arrival rate, 7.5 customers per hour arrive. And then about the service, it says an average of 4 minutes to service a car. And then we also see here that it is a single pump gas station. So I think those are the most important things that we identify when we look at problem in queuing theory. And there will be a pause in this video to give you more time to read this question. Same as before, first we define this queuing system in terms of a Candeli notation. Because the interarrival times and service times are exponential, we have mm here in the notation, and then we only have a single pump gas station. So it is one here, and there's no information about the other three characteristics, so we just write down GD infinity infinity. Okay, so that is the Candeli notation for this system. This is the lambda, the arrival rate, 7.5 customers or cars per hour. And then same with previous example, this problem does not give us the mu or the service rate directly. Instead, it gives us the 1 over mu. So 1 over mu, or the average service time, is 4 minutes. We would like to change it into hours, so it becomes 4 over 60 hour per car. So this is still the average service time. And then to convert it into service rate, we just flip it. So it becomes 60 over 4 or 15 cars per hour. So this is mu. It has the same unit with lambda. Finally, we can calculate rho, which is equals 1 over 2. The first question is very straightforward. We just need to compute L and W. And you just look at the formula for L and W for the MM1 queuing system and then plug in all the numbers that we've already got here. So whether you want to use rho or you want to use lambda and mu, that's fine. So just plug in the number and then you got this result. We may say that in the current system, it is unlikely to have a long lines because we only have one customer on average in the system. And then on average, each person spent around 8 minutes in the system. Now the second question says, suppose there is a panic buying. It changes the behavior of the customer such that people who are usually fill up when their tanks are exactly half full, due to the panic buying, they will purchase gas when their tanks are 3/4 full. So previously it is half full and then they purchase the gas. But now when it reached 3/4 full, they're already coming back to this station and then filling up their tanks again until it's full. So the question is how this panic buying has affected L and W. So we are still calculating L and W, but obviously the queuing system has been changing due to the panic buying. Let's take an illustration here. So this is the normal condition, and let's say we're looking at a 2 days period, and then we have this panic buying here, and then we're looking at the same 2 days period. In the normal condition, suppose we just fill our tank up to full, and then in 2 days we will return or come back to this service station to refill the tank and becomes full again. So this happens within 2 days. But now when panic buying happens, what we did is that now it is full, After we spent a day, it's already 3/4 now here. So this is 3/4 full up to this point. And then we will return to the station to refill it into full again. And then the next day, after we spent that much, we will return to the gas station again to refill it until full again. So now in the same period of 2 days, instead of coming into station once, now we are coming to the station twice. Okay. So in the same period, whether it is 2 days, 2 weeks, 2 hours, and whatever, so in the same period of time, now the panic buying causes all customers coming into the service station twice as much as before. So 2 times more often than before. Usually once every particular time period, now it becomes twice. So what changes here? The changes is in the arrival rate. When previously we have 7.5 cars per hour, now it becomes 2 times 7.5 cars per hour because the arrivals double in the same time period. Okay, so the lambda doubles, but then we have the information here that the service rate now becomes, so again, this is 1 over mu, and then we will convert it into mu. So now this is the new mu, which is 18 cars per hour. So now we have the new rho, which is 5 over 6. So let's use these values to calculate the new L and W. So here's the lambda, mu, and rho for the normal condition. And then these are the values for lambda, mu, and rho in the panic buying condition. Now we're going to calculate the L and W for the panic buying condition. So just plug in the number, and then we see that if panic buying happens, the W increases quite a lot from just 8 minutes to 20 minutes. So now during the panic buying, each customer on average spends 20 minutes in the system. I think the key point to solve this example is that we need to realize how we interpret the story about the changing behavior due to the panic buying to the change in lambda, which is now becomes 15 and previously just 7.5. So we translate that the panic buying behavior will double the arrival rate because it is not explicitly stated in the problem. So we have solved this problem, and then we have another example coming in the next video. So see you in the next one. Thank you.